Hi guys, Mrs. Delisin here. Welcome to another lesson of Algebra 2. Today's lesson is Rationals 3, Graphing Rational Functions. We will learn how to determine the domain and range of the parent rational function, and we will also learn how to graph the parent rational function. In this lesson, we will study how to graph rational functions. The simplest case or the simplest example of a rational function is f of x equals 1 over x. We are going to fill in the tables below, use the values to draw the graph of f of x equals 1 over x. So, as you can see, I already filled in the table, so we don't have to spend so much time on the video, but you can of course pause the video and copy and fill in the tables. So I started with my x value -5. So what I did is I have 1 over -5, and of course I got a -0.2, and then I did 1 over -4, 1 over -3, and so on. All right, and so here are the values. I have here also if when my x values are in decimal, so -0.5, -0.3. All right, so let us fill in. I know it's kind of like a lot to plug in all of these values, so let's focus on the values that are maybe like easy to plug in, like whole numbers or like half, because it's kind of hard to look at where's 0.3. Yeah, so let's focus on those, and then over here, like the ones that are over here, maybe I can even use 0.25 is fine. All right, so let's plug that in. Let us do -1, comma 1, -1, comma 1. I have 1, comma 1, 2, comma 0.5, 2, comma 0.5. I have, that's it, or maybe I can add this one, 4, comma 0.25. 4, comma 0.25, really small over here. Yeah, and then on this side we have a, what do we have? A -2, comma -0.5. We have -0.25, comma -4, -4 right over here. We have 0.25, comma 4, 0.25, comma 4 right in this corner. We have 0.5, comma 2, 0.5, comma 2, 1, 2 right over here. All right, and all we have to do is connect the points. So let's see if we can connect the points. I can connect these points, or maybe we'll make that smaller so we can see the flow of there. Keep go. So as you can see here, I can also connect that. Oop, it touches. There you go. There. Yep, as you can see, we have a pair of graph, right? We have on the right side, we have its own different graph, and then on the left, we also have a different graph in here. So here we have going this way, and then we have going this way, increasing, and then we have that, and we also have this one, okay? If you notice, this graph is not touching this line. So I'm going to make that red so we can see what is going on. Why is it not touching the y-axis? And why is it not touching the x-axis? Right? It's weird, yeah? This graph is weird because it's not touching the x-axis, it's not touching the y-axis. But first, we are going to talk about why is it not touching the y-axis? Why this graph is not touching the red line. So, number 2, what happens to f of x when x is 0? What happens to f of x when x is 0? So why don't we plug that in? What happens if our x is 0? So we're going to have 1 divided by 0. And what will happen is that it will be undefined. Because remember, we are not allowed to have a denominator that will be equal to 0 or a denominator that is 0 in this case. Undefined because you can't divide by 0. And if you take a look at my x values in here, the 0 is not in it. Because if I put a 0, let's put a 0 in here, it will be undefined, right? We cannot, it will be undefined, it will be error. We can't solve it when the denominator is 0. And so, that is why our graph here is not touching when x is equal to 0. Because this line is when x is equal to 0. And in the next slide, we will call this one our vertical asymptote. So what is that? But for now, let us study our graph first. What is the domain? The domain of f of x equals 1 over x. The domain of a function, is the set of inputs, all possible numbers that could be used as an input value. So in here, as you notice, let's do x such that x, okay, it looks like we can use all the values here. So we have positive x values, we have positive x values, we have negative x values, we have negative x values. So, but what we don't have is that we can't have an x is equal to 0. So for our domain restriction, our x can be anything, but it cannot be equal to 0. Okay? Moving on. What is the range of f of x? 1 over x. The range of a function is its set of inputs, all possible numbers that could result as an output value. So, let's see. I have positive y's, right? Because the y's of these points, these dots, are all positive. The y's of all of these dots are negative, but it looks like I don't have a 0. Right? I don't have a dot that has a y equal to 0. So in here, my range is f of x. F of x can be anything, but it cannot be 0. Okay, so that's my range. That's my domain and range for numbers 3 and 4. All right, here, in this slide, we will learn how to determine the domain of a rational function. We will also learn how to determine the vertical asymptote or asymptotes, because sometimes you have two, of a rational function. So, if you look at the graph that's given here, there is a red line. Let me point that. There is a red line in between where x is equal to 0, right? In this lesson, we will examine how to determine the vertical asymptote. The graph of the corresponding rational function will be given in each example, though we will not deal with graphing until a later lesson. So here, if we draw a vertical, remember that this x cannot be 0, right? There is a domain restriction. We learned that in the previous lesson. There is a domain restriction where x cannot be equal to 0. If we draw a vertical dashed line where x equals 0 is, we see that the graph of 1 over x gets closer to the line, but it will never touch it, or it will never cross it. This is an example of what is called a vertical asymptote. So how do we get the vertical asymptote? So let's have another example here. Determine the vertical asymptote of the graph of f of x equals 1 over x minus 2. Then, state the domain of the f of x. First, remember that the domain restriction comes from the denominator. So let us make that denominator equal to 0 so that we can determine the domain restriction of it. So here, I have x minus 2 equal to 0. X is equal to 2. Thus, our graph will not cross, will not touch x is equal to positive 2. Thus, the vertical asymptote of f of x is x is equal to 2. A line where the graph will not touch, will not cross. So if you notice in here, I have a vertical red dashed line up and down, right, where x is equal to 2, because that is what we call my vertical, I'm going to call it my VA, my vertical asymptote. So where do I get the vertical asymptote? I will get it from making the denominator equal to 0 and solve for the value of x. Now, what's my domain? My domain, my x values, or the set of inputs, can be any number. It can be any positive number. It can be any negative number. But I have a restriction that it cannot be a positive 2. And that's the reason why I have my domain as x cannot be equal to 2. Okay, moving on. In here, I have two sets of denominator. I have an x plus 2 and an x minus 3. So what I will do is I'm going to make both of them equal to 0. And I have x is equal to negative 2 and then x is equal to positive 3. Therefore, my vertical asymptotes are x is negative 2, x is equal to 3. These are the point of the graph that you cannot cross, you cannot touch. So the graph will get closer and closer to it, but it will never touch them. So if you notice here, there is a vertical red line coming over here at x is equal to negative 2. There is also a vertical dashed line at x equals positive 3. And those are what we call our vertical asymptote. And for my domain, I can use any negative number, I can use a 0, I can use any positive number. But there are two numbers, there are two x values that I am not allowed to use. Because when I use these values, the whole bottom becomes a 0 and the whole problem becomes undefined. So my domain, x cannot be a negative 2 and x cannot be a positive 3. Okay, let's have our example. Determine the vertical asymptotes of the graph of f of x, then state the domain of f of x. Let's start with looking at the denominator and making the denominator equal to 0. So I have an x minus 4. I have an x minus 4 equal to 0. Add 4 on both sides. I have x is equal to positive 4. So my vertical asymptote is x equals positive 4. And so my domain would be, I can use any positive number, any negative number. I can use a 0, but I cannot use a positive 4. Because when I do, the whole entire bottom becomes a 0. All right, let's try to graph that. And I would actually require you to draw the graph in your homework. There you go. Let's see if we can draw a straight graph. Yes, easier here. And so let us draw a dashed line. 1, 2, 3, 4 at x equals positive 4. And this is my vertical asymptote. Moving on, for number 2, I am going to start with looking at the denominator and making the denominator equal to 0. So 2x plus 3 equals 0. 2x equals negative 3. X is equal to negative 3 over 2. Or maybe I can use x is equal to 1.5 or 1 and 1/2. That doesn't matter. So our x is equal to negative 1.5 or negative 1 and 1/2. For my domain restriction, I can use any number, any positive number, any negative number, including 0, but I cannot use a negative 1.5 because if I do, that will make my whole entire equation undefined. So, where's negative 1.5? Let's draw a vertical line at a negative, oh wait, I think more, yeah? More to the left. There. This is my vertical asymptote. Okay, two more examples. I have 1 over x plus 2 and x minus 2. So I have two pairs of my vertical asymptotes going on here. So x plus 2, I always forget to change my color. X plus 2 equals 0. X is negative 2. X minus 2 equals 0. X is equal to 2. So our vertical asymptotes, and I need it to be written it this way. X equals negative 2. Oh, why do I have that? X equals negative 2 and x equals positive 2. Okay, it has to be written that way or else I'm not going to give you full credit. Because these are two vertical asymptotes, I want it written differently. Like x cannot, and x is equal to negative 2 and x is equal to positive 2. For my domain restriction, you can just write that one with a comma in between. That's fine. Technically, what this means is that your set of inputs can be any number except negative 2 and a positive 2. So I'm going to draw my vertical asymptotes here. Let's draw our line first. And because you have two sets of vertical asymptotes, you're going to have one at x equals negative 2, and you're going to have one at x equals positive 2. So this is what we call our vertical asymptote. And I will repeat, vertical asymptote is a line, a vertical dashed line. Technically, when you actually use a graphing calculator, you will not see a vertical dash red line, okay? It will not be in there. But it's technically like an imaginary line where you cannot touch, you cannot cross. But because when we touch negative 2, right? And this is negative 2 plus 2, the whole entire bottom becomes 0. And that's why we are restricted to use negative 2 and a positive 2. And that's why we draw a dashed line in it so that when we graph later on in the next lesson, we will be reminded that we cannot touch and we cannot cross that line. Okay, moving on. I have x plus 5 equals 0. My x cannot be a negative 5. And then I have also on the other side, I have x minus 3 equals 0. My x cannot be a positive 3. So my vertical asymptotes are negative 5 and a positive 3. For my domain, I cannot use negative 5 and a positive 3. Okay. Next one here, we have, let's draw 1, 2, 3, 4, 5. So a vertical dashed line representing my vertical asymptote. 1, 2, 3. A vertical dashed line representing my vertical asymptote. There you have it. So today we have learned what the rational graph looks like, the parent function 1 over x. We also have learned how to determine our vertical asymptote. We also learned how to determine the domain of our rational function. All right. I hope that you will be able to do your homework. And if you have any questions, please let me know. Thank you, and I'll see you guys on the next video. Bye.